Just going to look at some past HSC questions, some of them quite old, as you can see, but just from some different questions that have appeared over the years. I like the 92 one because it's actually an example of variable angular velocity. And you know, when it actually happened way back then, people sort of went, hang on a sec, variable angular velocity, the syllabus says it's constant angular velocity. How can you put a question in variable? It's still constant angular velocity because what happens in this one is our train's moving around this circular track. It's moving, when we refer it to zero, with constant angular velocity. However, when we refer it to a different point over here, n, that angle would change depending on where t is, but it won't be moving at a constant rate. So the actual train itself is moving with constant angular velocity, although they've quoted the linear speed of u meters per second, but that of course means if the linear speed's constant, well then the angular speed also has to be constant. So basically, this is just setting up the question, telling us all the dimensions. There's the angle theta, and so on. The first part of the question was to find d theta to t. Find that, and remember, theta is simply the angular velocity of the train, so the actual constant angular velocity. But we want it in terms of a and u. Well, we know that the length is a times theta. Differentiate both sides, and there we go. U was the velocity. I mean, whether you could have simply have just gone v equals r times omega and sub straight in. You could have done that and then said, oh, well, hang on, omega is the theta to t, v they told me was u, and the radius was that. Possibly I could have done it that way as well. So nice little gift mark, I guess, to start this question off, as opposed to this next bit. A little bit more involved. They want us to show this a sine theta equals 0, and then deduce that the rate of change of phi, it's certainly not constant. It's that expression there. So all right, the first bit. Well, again, I haven't got the picture there, it's on the slide before, but you've got it in front of you. I can set up some angles here. Angle NTO plus TNO would be TOS, exterior angle of the triangle. If I subbed in the theta and the phi, I get that angle NTO is theta minus phi. Basically, I wanted to identify where exactly is theta minus phi. I mean, they've put it in the final answer there. Okay. And so now all I'm using in triangle NTO is the sine rule. If you now look at that triangle, a over sine phi is a plus x over sine theta minus phi. And in fact, that is what they've asked us to show, but they've just rearranged the sine rule. So it wasn't immediately obvious that they were simply saying, hey, what's the sine rule? That's really all that first bit's saying. So when you rearrange it, there's the answer. So it's simply the sine rule, but also, I guess, working out what the size of angle NTO was. So you could use the sine rule. And from there, we now have to find d phi to t. Okay, so I'm going to differentiate that expression with respect to t. So a cos theta minus phi, well, sorry, it was a sine. When I differentiate sine, I get cosine, but can't differentiate it with respect to time. I can differentiate it with respect to theta minus phi. So by implicit differentiation, I have to multiply that by d theta minus phi dt. I've done two steps in one, I guess, here. So I had d theta minus phi dt, but remember, when you have several terms, you can differentiate individually. It's like saying, differentiate x squared plus x with respect to x is the same as saying, oh, differentiate x squared with respect to x plus differentiate x with respect to x. And so that's what I've done here. I've said, well, I've got d theta minus phi dt, and I'm going to split that and say, oh, well, that's the same as going d theta dt minus d phi dt. So that's just implicit differentiation. And then the next bit, we got a plus x cos, well, again, it must have been sine, differentiate sine, but I can't do it with respect to time. I can do it with respect to phi, implicit differentiation, so multiply that by d phi dt. So I guess that was the tricky bit there, is realising how to differentiate that. Now I just want to make d phi to t the subject of this equation. So if I group everything together with d phi to t, I've got an a cos theta minus phi minus an a plus x cos phi. All of that's times d phi to t. And the only other term I've got then is the a cos theta minus phi times d theta to t. All right. Well, let's move that to the other side, but you'll notice the other thing that I've done, d theta to t, remember back in part 1, we said was u on a. So I've changed the d theta to t to be u on a. The a's will cancel there. Remember, we're trying to make d phi to t the subject. So now, if I divide by the left-hand side, I've got the expression that they want. So the difficult bit of that, I guess, was knowing how to handle that differentiation. Well, we now have to show that that d phi to t, because remember, it's not constant. It's going to be variable. It's going to be 0 when nt is tangential to the track. I'm just going to redraw that diagram then. So if nt is a tangent to the track, we know that the radius is perpendicular to the tangent. So NTO, that's 90 degrees. So theta minus phi, because remember what he said, angle NTO was theta minus phi, that is 90 degrees. So if I sub that into d phi to t, I get u cos 90 on the top. Well, I don't really have to worry about the bottom now, because the cos of 90 is 0. So I've got 0 on the top of the fraction, so d phi to t is 0. So we've got that bit. Well, they're now saying let's let x equal a. Okay, so that distance x is the same as the radius of the circle. We're going to look for its angular velocity when theta is pi on 2, angular velocity when theta is equal to 0, and show that the first one's 3/5 the second one. So first of all, let's have a look when it's pi on 2. Well, when it's pi on 2, the angle at the centre now is 90 degrees. Remember, t and o was equal to phi. OT is the radius of the track, so we know that's equal to a. ON now is 2a. It was a plus x, but we've just been told x is equal to a, so that is 2a. I'll need the hypotenuse as well, because we're going to be dealing with sine and cosine. It'll work out to be root 5a. So from there, I can get an expression for cos phi. It's 2 on root 5. Cos of pi on 2 minus 5, which is angle NTO, and that's going to be 1 on root 5. So I substitute that in, so the cos of pi on 2 minus phi, and so on, sub those all in, and we get a value of u on 5a. It all comes out to be. Okay, that's the value when theta is pi on 2. We now want to work out what happens when theta is equal to 0. Well, when theta equals 0, we're basically talking about a straight line now. Because if you have a look at your diagram, that angle theta, if it's 0, we've got a straight line. So if that's 0, t is over here at s. So we've got a straight line we're talking about. So the angle phi will be with 0. And up here, that angle here would also be 0, because when we move it down here, again, we're getting 0. So when I substitute in, well, it's now just cos 0, cos 0, cos 0. Cos 0 is 1. I get u on 3a. Remember, we're trying to show that this one, no, sorry, the first one there is 3/5 the second one, which is the same as saying this one is 5/3 the first one, which is what I then did. I said, well, hang on, that is 5/3 of u on 5a. So yes, the angular velocity is 3/5 times the angular velocity when theta equals 0. The yo-yo question. A string of length L is initially vertical, so we're just hanging it down. It's got a mass m attached to it. Okay, so we're basically spinning it in a circle. That's what's... So it's a vertical circle. That's what we're dealing with here. So the forces involved, we'll have tension up the string, we've got the force due to gravity, and so on. So for parts A to D, we're assuming that my velocity is enough that that moves into a nice circle. We're going to show that the tangential acceleration is that lovely expression over there. Now, you might not recognise it, but well, no, I won't spoil the surprise. I'll say it at the end. It actually is a familiar result, although it doesn't look that familiar. Right. We know that the length is equal to the radius times theta, so the dimensions they've given us, S is the arc length, L in this case is now representing the radius, so S is L theta. So the linear velocity, ds to t, will become L times to theta to t. So the second derivative of S with respect to time, well, we know that's the derivative of velocity with respect to time. And, I might just play around with that because my answer's got to theta, not to t. So I'll get to dv to t and change it to dv to theta times to theta to t. Now to theta to t, somewhere, here we go, I could rearrange this over here, that's v over L. So I'll sub that in for d theta to t. So I have 1 on L times dv to theta times v. But hang on, v I could write as d to v over half v squared. And I have the result. All it is acceleration is d dx over half v squared. But it's times the length of the string because the length is equal to r theta. So it's that same idea. So it's that same equation, but now we're talking about the angular change, so the theta. So we're now going to show that the equation of motion is this lovely expression here. So what I'm saying is I'm going to get this picture and I'm going to rotate the picture so tension looks horizontal. Okay? So we rotate that picture, tension looks horizontal, but it now means gravity is going off at an angle. So we're going to have to break that up into its components, horizontally and vertically. Okay. I'm just looking at the ones that look vertical. And I guess the reason I did that is because, hey, there's no mention of tension in my answer. So if I go what looks vertical, I'll get no component of tension at all. So all I have is mg sine theta. It's the only force there that looks vertical. So the resultant force, mass times acceleration, will be the negative, because it's in the opposite direction, mg sine theta. But we just said that s double dot, or the acceleration, we just proved it was 1 on L d to theta over half v squared. So I'm substituting that straight in for the acceleration formula. From this, we're going to deduce that capital V squared is little v squared plus 2gl, 1 minus cos theta. We now know 1 on L d to theta of half v squared is minus g sine theta. So d to theta, I just multiply by L, basically. If I integrate both sides, I'll get a half v squared is gl cos theta plus some constant. I've actually done it as an indefinite integral for some reason, but anyway, it doesn't matter. Let's find those constants. So when theta was equal to 0, velocity was capital V. So subbing in constant turns out to be v squared minus 2gl. Subbing back in, and the result just drops out nicely. Explain why t minus mg cos theta is 1 on L mv squared. And I know you love these explain questions. So all right, there's good old Bob. Remember we had tension going to the left, and mg cos theta. Let's have a look at horizontally, or what looks horizontally. The resultant force would be going to the left, but the resultant force would be the circular motion, because it's going towards the centre. So in this case, mx double dot, I can replace with mv squared on, well, normally we'd say r, but they've said r is the length of the string L. So mv squared on L is equal to t minus mg cos theta, and I just rearrange that. So D was really just resolving the forces horizontally. Suppose that v squared is 3gl. Find the value of theta when this tension is equal to 0. So tension is now equal to 0. And what else have I done? I've substituted in for v squared, the expression that we found in part C. So I've got capital V squared minus 2gl 1 minus cos theta. But they've told me tension is 0, so I've subbed that in. So v squared is 3gl, which will cancel with the minus 2gl that we've got there. So minus mg cos theta is now mg plus 2g cos theta. And we will get cos theta is minus a third. They've said find the value of theta. So it's about 1.911 radians. Consider that situation. Briefly describe in words, because you love doing it, I know you do. The path of P after the tension T becomes 0. It's projectile motion. Projectile motion. Because you're going in a circle, okay, so it's travelling in a circle, tension's tight, now tension's disappeared. So what really are we doing? We're projecting an object now at a certain angle with a certain velocity. So it'll go like a parabola until, you're right, at some point, this will come tight again and it'll go back into the circle. So, see if I can do this. That might be easier. So, I might have got a bit carried away with my definition, my description, sorry. So when t equals 0, the particle's now going to go under projectile motion. So it's going to, like a parabola, it's going to follow a parabolic arc. So its initial velocity would be tangential to the circle. I actually bothered to find what it, as I say, this might have been overkill. I actually went and found the velocity, square root of GL on 3. And then I drew a picture and said, hey, look, we started down here and we kept going until tension became 0. And at that point then, we shoot off at a tangent and it becomes a parabola. But then at some point, it'll kick back into the circle. And so it'll have this weird path. Not actually a circle, it'll go along a circle, into a parabola, back into a circle, into a parabola, and so on, and so on. What a great question, eh? All right, now for the fun one. Speaking of projectile motion, you might remember back when I talked about projectile motion, I mentioned, well, our model, it's not actually a parabola in reality because there is actually resistance. So in 2003, they came up with this question. It's projectile motion, but taking resistance into consideration. You see, we don't actually get a parabola. We get this interesting curve there. They've given us the accelerations to start off with. It's the same as normal, but with resistance going in the opposite direction. So you get some constant times the velocity. So remember, it used to be we started with projectile motion. It was simply x double dot was 0, y double dot was minus g, but now this is saying, but there's also going to be a resistive force. So we're going to have this minus k x dot, minus k y dot. You are not required to show these, okay? Make sure you read instructions like that. All right. We're going to derive velocity and actually come up with this expression here. Okay. So we know acceleration, which is dv to t, is minus kx dot. This time I did do it as a definite integral. So if I integrate this, I've separated the variables, haven't I? But on the left-hand side, I knew that the 0 to t just ends up being t, and I did that all in one hit. So I've sort of done 2 steps in one there. I've separated the variables, but worked out the left-hand side at the same time. Well, that's just a log function. So minus 1 on k, the log, substituting x dot, substituting u cos alpha. Now we're looking to make x dot the subject. So I'm combined it into one log, multiply by the minus k, exponentialize both sides, then multiply by u cos alpha, and I've got the final expression there. Verify, and I've got to be honest, this is where I should have read the question carefully, because it says verify that satisfies the appropriate equation of motion. I actually derived it, so I went and said, oh well, dy dot dt is equal to minus ky dot minus g. Again, separate the variables, integrate both sides. We've got a log function again, And playing around with this one, eventually, when I make it all the subject and move terms across, I get it. That was probably a long way of doing it. To verify it, all I had to do was differentiate with respect to time and show that I got the result. Oh, that would have been quicker, wouldn't it? Okay. Should have read the question. Okay. Find the value of t when the particle... Now, these sort of questions still are exactly the same now. That, it reaches maximum height when y dot equals 0. So I have to solve it. I guess that's why they said verify this was the equation. So that way, if you couldn't get it, at least you could now go and do part C. All right. Now, I suppose one of the advantages of making this mistake is I already have an equation over here for time. And so I just used that. So if I sub in, I get the expression. What is the limiting value of the horizontal displacement of the particle? Okay, there's x dot. We're trying to find limiting value. Well, dx to t was u e to the minus kt cos alpha. So if I integrate both sides, x will equal, but I'm interested in the limiting value. So going from 0 to infinity, e to the minus kt, we're finding limits. I can't actually substitute infinity in. So I should really have a t at the top of that integral sign. U cos alpha over k minus e to the minus kt plus 1. Negative exponential as t approaches infinity goes to 0. And we eventually get it. So there's, 3 questions in Cambridge they have there. There's some more in Patel to look at.